Imagine a level 4 autonomous vehicle cruising down a highway. Every internal system is green. There are zero software bugs and no mechanical defects. But as it approaches an empty tunnel, the vehicle slams into a panic stop, nearly causing a pileup. For decades, automotive safety engineering has been governed by ISO 26262, the standard for functional safety. It assumes danger comes from inside the machine. It is designed entirely to prevent hardware and software faults, like a broken wire or a memory leak. Engineers solve these internal faults through redundancy. They build architectures with dual-core microcontrollers continuously cross-checking each other. If one component fails, the system detects it and safely degrades. But the vehicle stopping at the empty tunnel had no internal faults. Its microcontrollers were processing data flawlessly. The issue was that the radar waves bounced off the metal framing of the tunnel, and the computer accurately processed that corrupted echo as a solid brick wall in the middle of the lane. The hardware did exactly what it was programmed to do. The environment simply generated variables that tricked the physical limitations of a perfectly functioning sensor. To engineer around this, the automotive industry uses ISO 21448, the safety of the intended functionality, known as SOTIF. This table highlights the conceptual divide. While the left side focuses on broken internal parts, SOTIF targets the right, functional insufficiency. This occurs when the physical limits of a sensor collide with an environmental edge case, causing unsafe behavior without any internal failure. Reaching level 4 autonomy requires shifting our engineering focus past electrical shorts to mathematically bound the unpredictable physics of the real world. The core problem in SOTIF is that the physical world is infinite. You cannot validate a system against unknown, unsafe events by simply driving millions of test miles and hoping you encounter them. Engineers must translate reality into a strict, searchable data hierarchy. The absolute base layer of this hierarchy is the scene. Look at this diagram. A scene is a static snapshot frozen at a specific time, t. Every environmental variable is fixed: precipitation rate, asphalt friction coefficient, object placement. Time is 0. A single snapshot doesn't cause a crash. Action requires duration. By linking multiple scenes across a time axis, or delta t, we generate a scenario. We introduce motion, cause, and effect. A valid scenario must have defined starting conditions, a specific triggering event like another vehicle cutting into the lane, and an end condition. The highest tier of this ontology binds sequences together into the use case. It defines the broad functional goal, like a highway lane change, acting as a container for thousands of simulated scenarios. By forcing the environment into this structured hierarchy, engineers can use software to generate millions of permutations, hunting down precise edge cases that human test drivers would likely never see. Structuring the data is step 1. Step 2 is evaluating how the vehicle's computer processes it. SOTIF models this through Micah Ensley's framework of situational awareness. Level 1 is perception. The system detects raw geometry and movement, returning basic points in space. Level 2 is comprehension. The computer applies semantic segmentation to classify those raw points, determining that a specific shape is a pedestrian and not a mailbox. This visualization shows the hardest engineering challenge in SOTIF. Level 3, prediction. The system must forecast future states by generating a probability distribution of where that pedestrian might move next. When the computer's calculated probabilities fail to align with actual human intention, a misprediction occurs. The system either reacts too late because it assumed the pedestrian would stay on the sidewalk, or it slams the brakes for no reason at all. This is a direct functional insufficiency. An autonomous vehicle's safety boundary fails not when its cameras go blind, but when its statistical assumptions about the future collapse. These mispredictions are usually initiated by triggering conditions, specific environmental anomalies that force sensors to output corrupted data. Consider the optical limits of camera sensors. Modern traffic lights use LEDs that rapidly pulse via pulse width modulation. If that pulsing frequency mismatches the camera's shutter speed, the resulting frame captures the light when the LED is off, rendering a bright red signal as completely dark to the computer. Radar sensors are governed by a different set of wave propagation limits. This diagram illustrates a multipath error. The radar wave bounces off a metal guardrail, hits a flat manhole cover, and scatters back to the receiver. The altered time of flight calculation forces the system to plot a ghost vehicle directly in the driving lane. Even LiDAR, which maps environments in precise 3D point clouds, is bound by the physics of photon absorption. Look at this return intensity chart. Automotive black paint absorbs the infrared pulses used by many LiDARs. While a white vehicle reflects enough light to be tracked at 200 meters, the return signal from a black vehicle drops below the detection threshold at just 50 meters. This physical absorption drastically shrinks the system's safe stopping distance, doing so without triggering a single fault code in the vehicle's diagnostics. The danger compounds under a multiple-point functional insufficiency, the exact moment two or more of these sensor limitations align simultaneously in the environment. We cannot rewrite the laws of optics and electromagnetism. Engineering safe autonomy requires designing architectures that anticipate these exact physical failures. This brings us to the operational design domain, or ODD. This is the struct perimeter of weather, speed, and infrastructure conditions the vehicle is mathematically certified to handle. When sensor physics break down and the environment pushes past that perimeter, the vehicle is forced into an OD exit. The system manages this transition through a state machine, starting with a look-ahead check. It predicts an upcoming boundary breach and issues a warning. If conditions deteriorate, the system issues a takeover request, giving the driver a countdown to assume manual control. At this stage, SOTIF requires engineers to account for human psychology, specifically analyzing what is called reasonably foreseeable misuse. This distinguishes between unintentional misuse, like falling asleep, and intentional abuse, like clamping a weight to the steering wheel. If the driver fails to take the wheel, the logic routes here. The vehicle seizes final control and initiates a minimal risk maneuver. The MRM dictates a sequence of emergency decelerations and lane changes to pull the vehicle out of active traffic. The maneuver ends only when the vehicle achieves the minimal risk condition: complete stoppage, parking brakes applied, and systems locked down. Building a system that drives is only half the engineering challenge. SOTIF demands mathematical certainty in how that system handles its own technical limitations. SOTIF forces the automotive industry to permanently abandon the engineering fantasy of an omniscient, error-free machine. We structure data into use cases, anticipate probability mispredictions, measure the hard physical limits of our sensors, and enforce strict state-machine logic to bound the system. This methodology moves engineering from a reactive fail-safe posture, waiting for hardware to break, to a proactive safe-by-design discipline. Instead of chasing an absolute guarantee of zero accidents, SOTIF benchmarks the system against the absence of unreasonable risk, a metric grounded in statistical probability and physical constraints. Providing this verifiable framework of sensor physics and ODD logic creates the objective data required for regulatory certification. By documenting exactly why and how a vehicle remains safe under duress, we provide the technical evidence necessary to move autonomous driving into the public domain as a commercial reality.